All right, we're continuing, and next up we have Yoann with a rebirth of the the Plan 9 toolchain named Goken. And yeah, stage is yours.
Hi. Yes, so I'm going to talk about the Goken project, which I started about a year ago now. And so a little bit of background. And so the designer of Plan 9 didn't just rethink the kernel. So they rethought the whole software stack, the entire operating system. And so they rethink the windowing system, the graphics stack. But in particular, they also rethought the tool chain. And so the assembler and relinkers, which I think was written by Rob Pike and the compiler by Ken Thompson, is a different beast than the other tool chain. And so a few design decisions that they took is that usually the code generation is mostly in the assembler, and then the linker just patch things together. And actually in Plan 9, the code generation is not done by the assembler at all. All the code generation is done by the linker. And this change of responsibility, I actually think, is a good idea. It simplifies the code. Another decision was that Ken Thompson decided to embed a C preprocessor directly in the C compiler. So when you compile C code in Plan 9, it doesn't call the CPP C preprocessor. I mean, it can, but there's also one embedded inside, and so it saves the compilation time because you don't fork, you don't, and so that's another key design decision. And another key design decision was that they thought from 30 years ago, they thought from the beginning about making it easy to cross-compile. And so now, like this tool like Zig that claims that they make cross-compiling easy, 30 years ago, like the Plan 9 toolchain was already doing that. And so actually how they were doing it, that there's this simple naming scheme where every architecture was a different letter, a different character. And so you had the ARM was the character 5, the x86 was a character 8, etc. And so when you wanted to use the ARM compiler, you were just calling 5C. And 5C will produce object file with a .5 extension. And then when you will link, it would produce a 5.out binary. And because of that, there was no conflict. If you were using 5C or 8C, it will produce different object file with different file name extension. There was no file conflict. And so it was very easy to cross-compile for many architecture and to link for many architecture. And so in the rest of the talk, I will use the term Kencc for the Plan 9 tool chain. So the set of tools to support many architecture and to link, to assemble, and to compile. And so, yeah, one remarkable thing about the Plan 9 tool chain is that it's incredibly small. And so the assembler is about 3,000 lines of code. The ARM linker is 7,000 lines of code. The C compiler, and if you take the architecture independent and the ARM part, the ARM specificat is 18,000 line of code. So in total, if you take the full ARM toolchain, is less than 30K. And so to give a sense of scale, so on the right you have a tree map where every rectangle is proportional to the number of lines of code. And so GCC is 15 million lines of code. The binutils that you don't see, 700,000 lines of code. And so the little rectangle that you cannot very see well, that's the whole of Plan 9 actually. That's the whole operating system, not just the toolchain, the whole thing. So in less than 180K, you had everything inside. And so if you take GCC plus binutils, it's going to be million lines of code. Instead, Kencc for ARM is just 30,000 lines of code. So of course, GCC supports many architecture. Actually, Kencc also. But if you take the core of GCC, it's still far bigger than the Plan 9 toolchain. And actually, I remember I looked at one file in binutils for ARM that was already 30,000 lines of code. So one file in binutils was already more than the whole ARM toolchain. And so because it's small, actually Kencc had a life after Plan 9 4th edition. And so, because it was easy to understand and easy to modify. So after 2000, so after the 4th edition of Plan 9, Charles Forsyth, or Forsyth, I don't know how to pronounce it, Charles Forsyth, added support for ARM64 with the letter 7A, 7C, and 7L. And that's power modern Apple machine, and also the more recent Raspberry Pi, the 3 and 4 and 5, I think. Then I don't remember when, Richard Miller, again, added RISC-V support for the 32 and the 64 variants. So you have the letter I and G for that. So you have IC and GC. Then I don't know when, but the Inferno developers also extended Kencc, and what they've done is that they removed the plain specific C extension. So the dialect of C is special in Plain 9. It uses special extension, and so you cannot actually use GCC or Clang to compile the C code in Plain 9. But what they've done is that they focus just on the toolchain, just on the C compilers, assembler, and linker, and they removed all these special extension, and that allows them to use GCC or Clang to compile the Plain 9 compiler. And so then you could use the Plain 9 compiler on Linux, Mac OS, or I think Windows also. It would still produce binaries just for Plain 9 or Inferno, but at least you could build them on Linux, on Mac OS, etc. And then finally, in Go itself, so if you take the old version of Go, so less than 1.3, and so Go was designed by Rob Pike and Ken Thompson, who were the creator of Kencc, actually. And so they extended Kencc for Go, and so they added ELF support, but also really to produce binary for Linux. They added Mac-O binary format, which is like to produce binary for Mac OS. And they also added PE, the PE format, binary format for Windows. And so they were able then to modify Kencc to have a toolchain. I should need to modify that. To have a toolchain that could produce binary for Linux, for Mac OS, and for Windows. And so they also built a minimal C library so that you could also have a system calls whose binary could do system calls for Mac OS. And so that's why now for the Go programs that you compile, you can cross-compile them for many architecture, and they will work on all these different operating systems. But that was for old version of Go in less than 1.3. Later on, they rewrote this tool in Go itself, but in Go less than 1.3, it was like the original, basically 5C, 6C, 8C that were inside the Go repo itself. And so the idea of the Goken project is to take all these different improvements that were a bit spreaded and to put them in one repository and to support every modern architecture. And so the goal is to target modern architecture, and so to be able to produce binary for ARM64, AMD64, and RISC-V. The goal is also to build and run on those architecture. That is, I want to be able to run those Plain 9 toolchain on Plain 9, but also on Linux, also on Mac OS, also on Windows. And I want to produce binaries for all these 4 OSs in these different architectures, so that I can have effortless cross compilation, so that I can be on my Mac laptop on Mac OS and produce binary for RISC-V Linux. And so the URL on the right on GitHub is the URL of this project, of this Plain 9 toolchain. And so what's inside Goken today? And so basically I took some of the components of the Plain 9 toolchain that was in the 4th edition of Plain 9. And so there's a MIPS toolchain, the ARM, x86, and AMD64. I took the work of Charles Forsyth, and so you have the ARM64 toolchain, and the work of Richard Miller. And then I've taken some of the Go extension that they made to support ELF, Mako, PE. They also had support for, in this Go work, they also added support for the dwarf debugging format. So you could produce binary and then use GDB to debug those binaries. You could also use ACID and DB, but you could also use GDB. And so another thing that I've added is that I've added a portable minimal C library, which is inspired by lim9 in Plain 9 port, so that you can, basically the code that, thanks to this lim9 library, the code is exactly the same than in Plain 9. That is, the compiler, the Plain 9 C compiler, is going to use some special system function from the libc of Plain 9, and it will work because lim9 is an adapter that will work on Mac OS, that will work on Linux. So that's mostly the work done by Russ Cox on Plain 9 port. I've also added the source of Lex and Yak and Ed, because they are part of to compile the Plain 9 toolchain, you need a Lex and a Yak and an Ed. And finally, it contains the portable variants of MK and RC that is POSIX compatible. So I can also, because you need MK and RC to compile this toolchain. And so how do you build Goken? And so this is a Docker file. So I hope everybody is a bit familiar with it. It's pretty self-explanatory, I think. But basically, this Docker file will specify how to build Goken itself. And so at the top, you see, so let's start from a Ubuntu container. And then you use this apt-get command to install GCC, the C library, and Yak. Later on, you run the /configure. So no worry, it's not autoconf. It's a very small script that just detects the architecture, whether you're on ARM64 or AMD64. So it's a very, very small script. And then you run this script build mk.sh, which is basically a very long script where every line is calling the GCC to compile one part of MK. Because there's no MK yet, and so you cannot use MK to compile MK, to build MK. So you have this flat list of commands, and that also build RC and head. And once you have this, you run this promote mk.sh, and now in your path, that you adjust later with path and mk shell, now you're in an environment where you can use mk and RC. And that's a nice world to be, because now you're in familiar territory for Plan 9 people. I have MK and RC, and that's when you run the mk and mk install command, and that will build the whole Plan 9 toolchain. So that will build 5C, 6C, IC, VC for MIPS, and also all the assemblers and all the linkers. And so the only thing you need to have this is that you need a C compiler, so GCC or Clang. It will work also with Clang. A linker, part of the binutils, for example, or with Clang it's going to be a LLD, and a POSIX shell for the build mk.sh script. And that's the only thing you need. And now this Docker file will work on Linux. It will also work on macOS, and it should also work on Windows. And once you have this, you've built a container. You've built a container that you're in familiar territory. You have like a tool chain. You have a Plan 9 tool chain. And so, for example, here, I'm in this, if I do which MK, that's the MK that is in the path from the Goken project. And now I'm in the Principia directory, which is a Plan 9 fork that I will explain tomorrow. And I can just run MK, and it will build the whole Plan 9 distribution. So it will call 8C. It also called PCC for ape. It will call IAR, which is like the AR program but that do not conflict with the host. And then it finished. And now you can also build a kernel. And it will build a query maker. Then you can make disk to make a DOS disk image. And then you can just do mkrun, and that will run QEMU with this Plan 9 distribution that is there. And you can run Rio if you want. Sorry. And you can even run Rio under Rio. But the idea is that you have a tool chain that can work on different OS. And where is my talk? Is here. Okay. And so, that's one of the use cases of Goken. It's to build Principia software that I will talk tomorrow. And so actually, how you need to support like a different bunch of host OS. So you want to be able to build on Linux, macOS, Windows, and Plan 9. With this, each time there's a different architecture. So Linux actually works on all this architecture. And you want to be able to target, that is to produce binary that can run on Linux, macOS, Windows, or Plan 9 with this different architecture. And actually the value in there are wrong. But right now, like the Goken can build Linux binaries for MIPS, for AMD. It can build binaries for macOS, but only an old version of macOS. Because the recent version of macOS, the binary format needs to be changed. But I took the code from Go 1.3, and so Go 1.3 was, I think, 15 years ago, and so in between, like, macOS changed. But it is doable. It's a lot of, so actually, like, the future work is to try to complete this big hypercube of a combination of configuration, it's not that complicated, but each time it's little detail like, macOS changed, like the system calls are a little bit different. Each time for each operating system, you need to find the right number, the value for each system call number. Open on Linux is 24 on MIPS, but it's 56 on ARM, and it's going to be a different value. So actually, the Go developer did that for each operating system. And so that's something we will need to repeat or just like steal, which is my favorite technique. And so you can expand right now it's just you can produce binaries that just use open, read, write, and close, which you can do a lot already with just the system calls, but that will need to be extended. I would like to validate this work on Raspberry Pi, on RISC-V board. And another thing is that right now Goken and Principia, Softwarica, were forked from different Plan 9 offspring, and so now actually I would like to merge them back, but and that's it. This is Goken.
All right, so we have about 4 or 5 minutes for a handful of questions, and again, please queue up here.
So the first thing that comes to mind that I'm inclined to want to use this for is to replace Russ's 9C script from Plan 9 port.
Yes.
Have you tried using this to become the native compiler in the Plan 9 port world?
Yes, so actually, Goken contains also some of the utilities like cat, ls, also troff, EQN, so some of the things that Plan 9 port is doing. So I was able to compile all these programs using Goken. I didn't try the whole Plan 9 port, but that's...
Excellent. And yeah. And the URL is in the paper?
Yes, it's github.com, Arix, and then Goken 9cc.
Good. I'm going to.
But yeah, there's lots actually. There's many fork of Kencc. And so like in 2015, actually, I did another fork called Fork Kencc. And then it was forked by someone else to add support for Richard Miller. There's also David Ducolombier, who was also a fork of the Inferno Kencc. So there's all these forks, and it's Nine Front also like added many things to the Plan 9 toolchain in between. So all these forks. So the goal of this was to try to have yet another fork. But the goal here is mostly to not just think about Plan 9, to also they can produce binary for macOS. They can produce, because I'm sad that for example, a long time ago I was trying to play with XV6, so it's a toy operating system, and I had to use GCC toolchain to try to compile it. It was hard. It was actually hard to use GCC to compile, to cross-compile for XV6. And so that's also part of the goal, to make it easy to cross-compile for this different operating system. And it's not that hard, I think, to make it work.
Excellent.
I guess question from the internet. Why in progress for for ARM64 on Plan 9?
No, but there's lots of things that I didn't test. Like right now, even like floats. Actually, a lot of time I spent right now to just make it to compile on AMD64, because in the source of the Plan 9 compiler, they're using long, which is also the case on 9 Front. They're using long for many things, and actually, if you GCC in the Plan 9 world, long is always 32 bits. GCC is considering long on 64-bit machine as 64, and that means lots of the code doesn't work at all, because when they assume that the long is 32 bits on ARM to compile ARM 32 bits, and now it's 64 bits, and lots of arithmetic operations on them are completely wrong now on 64 bits. And so I spend a lot of time, too much time, to try to make it work on 64-bit machine, actually. And float, for example, it should be simple, doesn't work right now very well. So I'm starting from toy C programs and toy assembly programs, and trying to support them on Plan 9 for MIPS, Plan 9 for ARM, Plan 9 for etc. I'm trying to add each time an architecture, but it takes time.
Are those size differences still present if you're using -f plan 9 extensions to the compiler? Because I know that I don't know if GCC supports that. I guess it does, but there is a flag that allows at least Clang, if I recall correctly, to support Plan 9 style C, and I thought that also applied to sizes as well.
I didn't try that. Actually, there's lots of flags that are needed, like even for SSE. For SSE also, like some of the assumption in the floating code in Plan 9 is different from the GCC world, and so it took a long time to debug that. And actually, you need this SSE2 blah 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 option. Otherwise, the floating code is using a different precision. It's using 48 bits instead of 64. I don't remember exactly why. So but I didn't know about this flag. But I wanted to change the long from long to int32 because also I think it's more readable to see the ARM code and that this flag is actually int32. It's not a long. It's really, and actually that's when the Go people extended Kencc. That's one of the first things they did, like Ken Thompson and Rod Pike and Russ Cox, was to transform many long into int32.
All right. Looks like that's it. So thank you.